Welcome to part 4 of our final exam review. In this part, we're going to actually work with looking at the inferential statistics, the very last part of the class. As I said in one of the earlier parts, this slide presentation was made by Dr. Davis, and she did such a fabulous job, and she's very generous to let us use it. So we're going to go through here and look at one sample inference. Now, we see we have our parameter. So we'll look in the second column, because the first column is going to tell us what's in each of the columns. So we're going to look at the mean when the standard deviation is known. What our null hypothesis will look like is mu equal mu naught. Now remember, we have 3 different hypothesis tests that could be possible. It depends on what we're trying to test. So if we're trying to test that we think the mean has increased, that's called a right-tailed test. So our alternative would look like mu is greater than mu naught. If we're thinking that our mean has decreased, we're in a left-tailed test and would look like mu is less than mu naught. If we think the mean has changed, but we don't know whether it's increased or decreased, we do what's called a two-tailed test. We just say mu just doesn't equal mu naught. Now the test statistic, when we know the standard deviation and all the assumptions have been met, then our test statistic looks like z naught, and that's x bar minus mu naught over the standard error, which is sigma divided by the square root of n. What we found there, the test statistic, remember, is how many standard deviations our sample mean is in the null hypothesis distribution. And remember, the null hypothesis distribution has a mean of mu naught and a standard error of sigma over the square root of n. Because inferential techniques that we use here for these parametric tests, we are in sampling distributions, so we have the standard deviation for our sampling distribution. Now the distribution that we're going to go to find our p-value is the standard normal. That's if all the conditions are met. If I'm going to do a confidence interval, then it looks like x bar plus or minus my critical value. The book uses z star, but remember I had used z alpha over 2 because that tells us a little bit more information about our confidence level, times the standard error. Now this was what we saw in chapter 14 and 15. So we're going to go to the third column, where our parameter is the mean, but this time the standard deviation is unknown. Our null and alternative hypothesis look exactly the same, but the test statistic has a different look to it. We see instead of a z, we see a t naught. What happens here is, since we don't know the standard deviation, we have to estimate it using the sample standard deviation. So we can no longer go to the standard normal tables, but the student t-distribution. And with that, we have to know, we go to table C. So our test statistic looks like x bar minus mu naught over, and the standard error here can't be sigma over the square root of n, but it has to be s over the square root of n. So again, we go to to table C for our student t-distribution. Our confidence interval is the way that we create our confidence or construct our confidence interval is we take the sample mean plus or minus our critical value in the student t-distribution times our standard error s over the square root of n. And that's a chapter 17 problem. That's when we worked with doing inferential statistics about the mean when the standard deviation was unknown. Now in chapter 19 we worked with the proportion. Our parameter was p. Proportion. Our null hypothesis will look like the parameter equaling p naught, because we're into proportions. And the alternatives will look exactly the same, except instead of a mu, you see p. Our test statistic, we're back into table A, into the standard normal. So if all the conditions are met, our test statistic looks like p hat minus p naught divided by the standard error, which is p naught times 1 minus p naught over n. The standard error of our hypothesis distribution. Now we're back into using table A, where we can find our p-value based on this test statistic. Now if we're doing a large sample confidence interval, if those conditions are met, n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Or in our class we were doing n times p times 1 minus p, both of those will work, being greater than or equal to 10. We can make our confidence interval p hat plus or minus our critical value, again, which is based on our confidence level times the standard error. But as you see, the standard error here, we don't know what p is, so we have to use p hat. So p hat times 1 minus p hat divided by n, take its square root. Then we construct our confidence interval. Now, if the conditions are such that we can use the plus 4 method, remember how that works. Instead of p hats, we're going to have these p tildes. And p tilde is x plus 2 divided by n plus 4, hence that plus 4 confidence interval. Because we add 2 to the successes and 2 to the failures, which adds 4 altogether imaginary data values in our whole sample. Now let's look at two-sample inference. The very last part of Chapter 17 dealt with two means, but these two samples were dependent, where person or thing number 1, whatever value we had there, would be person or thing number 1 in the second sample, or they're directly correlated. There's a dependence. Person number 1 directly affects who person number 1 is in the second sample, or thing number 1, thing number 2 kind of idea. So you have a dependence going on. What happens here is you're going to take those samples and you're literally going to take x1 subtracted from y1 and actually get a difference right there. And we're going to do an analysis on the differences. So that's why you see this mu sub d equaling 0. So we're going to say we're going to take the column of differences, take its mean and standard deviation, and work with that. So in our null hypothesis distribution, we're going to say there is no differences, that the SAT score before I do a prep course and the SAT score that I do after is 0. The prep course didn't work. I got the same score. But if it works, then my before SAT score should be lower than my second. So my mu sub d, my difference, I would expect, if it worked, should be a left-tailed test. So it would be mu sub d is less than 0. And you could pick scenarios where mu sub d would be greater than 0. And if we just don't know, if we're just testing to see if something made a difference, we'd do a two-tailed test. And our test statistic looks like T naught equaling d bar, the average of all those differences, divided by the standard deviation of those differences. We will give you S sub d divided by the square root of n. And then we get our test statistic. And we can find our critical values using t. Our degrees of freedom would be n minus 1, where n is the number of pairs that we have. Because you're going to have the same, you have to have the same sample size in sample 1 and 2, because these samples are dependent. And if I want to do a confidence interval, it's going to be d bar plus or minus our critical value t star S sub d over the square root of n, because the standard deviation is S sub d over the square root of n. Then we went into Chapter 18 where we had two means, but this is where the samples were independent. We don't have person 1 having anything to do with person 1 in the second sample. So what we're going to do here is we're going to take the first sample, we're going to calculate its mean and standard deviation, have the second sample calculate its mean and standard deviation, and then truly look at the difference of those two means. And so there you see what the null hypothesis and all the different alternatives would look like. Our test statistic looks like T naught equaling, and in the numerator you're going to have x bar 1 minus x bar 2. And if you subtract the value of the null hypothesis distribution, well, in our class we're always assuming that to be 0. Because look at our null hypothesis. If mu 1 equals mu 2, that means that mu 1 minus mu 2 equals 0. So we're going to continue in the next part with finishing up with the two means independent and go to the two proportions.